Did you know that everything you see, touch, and feel is mostly empty space? It's true! If you took all the empty space out of every atom that makes up every person on Earth, the entire human race could fit inside a single sugar cube. That sounds like something out of a superhero movie, doesn't it? But this incredible, mind-bending fact comes from a super strange and wonderful field of science. It's a place where the normal rules of our big world don't apply. This field is called quantum physics. It's the science of the very, very small. It's time to shrink down and explore this amazing, invisible universe that's all around us. This tiny world is a place of magic and mystery, but it's a kind of magic that scientists can study and understand. It governs the building blocks of everything. The atoms, electrons, photons. Think about the smallest thing you can imagine, maybe a grain of sand. Now imagine something a billion times smaller than that. That's the scale we're talking about. Before we start our adventure, let's get one thing straight. What exactly is quantum physics? Physics is the science of how things work, from giant stars to spinning tops. For a long time, we had one set of rules, now called classical physics. These are the rules figured out by amazing scientists like Isaac Newton. They are fantastic for explaining the big stuff, like why an apple falls from a tree or how planets orbit the sun. These rules are reliable and predictable. But then, about 100 years ago, scientists started looking at the super-duper small. They studied atoms and the tiny particles that make them up. And they found something shocking. Classical rules didn't work anymore. It was like using the rules of basketball to play chess. Tiny particles weren't tiny balls. They behaved strangely. A new set of rules was needed. Quantum physics, the rule book for the tiny universe. Think of it like this. One of the first and weirdest discoveries in the quantum world is something called wave-particle duality. I know it sounds complicated, but stick with me. Imagine your favorite superhero. On Monday, they are a regular person working a normal job. But on Tuesday, they are a powerful hero saving the world. They have two different identities, right? Well, in the quantum realm, the tiniest bits of matter, like electrons, have a similar split personality. Sometimes they act like a tiny solid particle, like a super small marble. They are in one specific spot and you can pinpoint their location. But other times, the very same electron acts like a wave. Think of a ripple spreading out in a pond. A wave isn't in just one spot, it's spread out over an area. It can go around corners and interfere with other waves, creating bigger or smaller ripples. Scientists discovered that tiny particles can do this too. They can behave as if they are spread out in space like a fuzzy cloud of possibility rather than a single point. This was a revolutionary idea because, in our big world, things are either particles or waves. A baseball is a particle. The sound from your speaker is a wave. They are never both. The most famous experiment that shows this is the double-slit experiment. Imagine shooting tiny marbles at a wall with two narrow slits in it. The marbles that go through will hit the back wall in two distinct lines, right behind the slits. That's what a particle does. But when scientists shot electrons one by one at two slits, something amazing happened. The electrons didn't create two lines on the back wall. Instead, they created an interference pattern, a series of many lines, just like you'd expect if waves were passing through both slits at once and interfering with each other. This was mind-boggling. It's as if each single electron traveling all by itself was somehow passing through both slits at the same time, like a wave, and then interfering with itself before hitting the back wall. But here's the craziest part. If scientists put a detector at the slits to see which one the electron went through, the wave behavior vanished. The electron would suddenly act like a particle again and just go through one slit or the other, creating the simple two-line pattern. The very act of observing it forced it to choose an identity. It's not just matter like electrons that has this split personality. Light does too. For centuries, scientists argued about what light was. Isaac Newton thought it was particles, corpuscles. Others thought it was a wave, sound wave, water wave. For a long time, the wave theory was winning. It explained bending and reflection. Then quantum physics showed they were both right. Light is both wave and particle. Wave-like behavior. Think soap bubbles, oil slicks on wet roads. Interference patterns create those colors. Wave nature also gives us radio. Radio towers sending long waves. Other times, light is tiny energy packets. Albert Einstein championed this. He named them photons. A photon equals a single quantum of light. Particle behavior powers tech. Seen a solar panel? They work because of light's particle side. Animated photons hit a panel like billiard balls. Photon smacks an electron and knocks it loose. freed electrons flow, electric current, that's solar power. If light were only a wave, it couldn't concentrate energy to knock electrons out. It needs particle power. So, wave when traveling, spreading and interfering. Particle when interacting with matter, delivering energy in one packet, like a secret agent, travels in disguise as a wave, then reveals its particle self to hit a solar panel or your eye's retina. This dual identity isn't a contradiction. It's the strange, wonderful quantum universe. Light is both, all at once. Now that we know particles can be weird, let's add another layer of strangeness. In our big classical world, we can know things with great certainty. If a car is driving down the road, you can measure its exact position and its exact speed at the same time. No problem. But in the quantum world, there's a strict rule that says you can't. This rule is called the Heisenberg uncertainty principle, named after Werner Heisenberg. It's one of the most famous ideas in quantum physics. The principle states that there is a trade-off. The more you know about a particle's position, where it is, the less you can know about its momentum. Momentum meaning mass times velocity, telling you where it's going and how fast. And the other way around is also true. Measuring momentum precisely blurs position. It's not because our tools are bad. It's a fundamental property of the universe. There's built-in fuzziness at the smallest scales. Why does this happen? Think about measuring a tiny electron. To see it, you must bounce something off it, a photon. The photon hitting the electron is like a bowling ball hitting a ping pong ball. The measurement gives the electron a huge kick and changes its momentum unpredictably. The moment you find exactly where it was, you have no idea where it's going. This isn't just a limitation, it's the particle's nature. A quantum particle doesn't have a single definite position and a single definite momentum at the same time. Its properties are blurry until we measure one. Measuring one property makes it definite and makes the other more uncertain. It's a cosmic balancing act, a fundamental I don't know woven into existence. It's humbling and mind-bending. So, if particles don't have definite properties until we measure them, what are they doing the rest of the time? This leads us to another core concept of quantum mechanics, superposition. Now, this sounds like a fancy word, but it just means that a particle can be in many different states or many different places all at once. It's not in state A or state B. Instead, it exists in a combination of all possible states simultaneously. It's like a cloud of probabilities, a smear of potential realities, all coexisting. It's only when we make a measurement that this cloud collapses into a single definite outcome. Let's imagine a quantum coin. Before you flip it, a classical coin is either heads or tails. You just don't know which one. But a quantum coin, while it's spinning in the air, is in a superposition of both heads and tails at the same time. It's not one or the other. It's a fuzzy mix of 50% heads and 50% tails. The moment it lands and you look at it, the moment of measurement, the superposition collapses. And it is forced to become either heads or tails. Before you looked, it was truly, physically, in both states at once. This idea is really at the heart of what makes quantum physics so different from our everyday intuition. In our world, a light switch is either on or off. You are either in the kitchen or the living room. But a quantum particle, like an electron orbiting an atom, can be in a superposition of different energy levels. It can be in a low energy orbit and a high energy orbit at the same time. It's only when it interacts with something, like absorbing a photon of light or emitting a photon of light, that it chooses a single energy level to be in. This ability to exist in multiple states at once is not just a weird theoretical idea. It's actually the key to building the next generation of super powerful computers called quantum computers. A regular computer bit is like a light switch. It can be a 0, off, or a 1, on. But a quantum bit, or qubit, can be a 0, a 1, or a superposition of both 0 and 1 at the same time. This allows quantum computers to explore a huge number of possibilities at once, making them incredibly fast at solving certain types of problems that would take a normal computer billions of years. To show just how strange the idea of superposition was, scientist Erwin Schrödinger came up with a famous thought experiment. It's not a real experiment. No cats were ever harmed. It's a story designed to make you think. Imagine you place a cat in a sealed steel box. Inside the box with the cat, there is a tiny bit of radioactive material. This material is so small that in the course of 1 hour, there is an exact 50-50 chance that one atom will decay. If the atom decays, it triggers a device that releases a poison. And the cat, well, the cat dies. Now here's the quantum part. According to the rules of superposition, until we observe it, the radioactive atom is in a superposition of both states, decayed and not decayed. It's both at the same time. But because the cat's fate is linked directly to the atom, that means the cat must also be in a superposition of states. Inside the closed box, before we look, the cat is not dead or alive. It is in a bizarre quantum state of being both 100% dead and 100% alive simultaneously. It's only when we open the box to check that the superposition collapses into one reality or the other. Schrödinger created this thought experiment to highlight what he thought was an absurd conclusion of quantum theory. How could a large, complex thing like a cat be in two opposite states at once? It makes no sense in our macroscopic world. This paradox gets to the heart of a big unanswered question in physics. Where does the quantum world end and the classical world begin? Why do atoms get to be in superpositions, but cats, people, baseballs don't? This is called the measurement problem, and scientists are still debating the answer today. Some scientists think that the active observation or measurement by a conscious observer is what causes the collapse. Others believe that any interaction with the larger environment is enough to decohere the superposition, forcing it into a single state long before a cat could ever be both alive and dead. Whatever the answer is, Schrödinger's cat remains one of the most powerful and memorable illustrations of just how deeply strange the quantum world is and how much it conflicts with the reality we experience every single day. It really forces us to ask what it even means to be something. If you thought things couldn't get any weirder, hold on tight. We're about to explore what Albert Einstein famously called spooky action at a distance. The official name is quantum entanglement, and it's one of the most mysterious phenomena in science. Imagine you have two entangled particles. You can create them in a lab so that they are linked in a special way. For example, you can entangle two electrons so that they have opposite spins. Spin is a quantum property. You can think of it as either up or down. If one is spin up, the other must be spin down. Now here's the spooky part. You separate these two entangled particles. You send one to the other side of the room and the other to the far side of the galaxy. They could be light years apart. According to the rule of superposition, before you measure them, neither particle has a definite spin. Each one is in a superposition of both spin up and spin down. But the moment you measure the particle here on Earth and find its spin is up, you instantly know, faster than the speed of light, that its entangled twin on the other side of the galaxy must have collapsed into a state of down. This instantaneous connection is what bothered Einstein. How could measuring one particle possibly affect the other one instantly, across such a vast distance? It seemed to violate the rule that nothing, not even information, can travel faster than the speed of light. He thought there must be some hidden information, hidden variables, that the particles carried with them from the start, like two gloves separated into boxes. Opening one box to find a left-handed glove doesn't magically make the other one right-handed. It was right-handed all along. But incredibly, experiments have proven Einstein wrong. There are no hidden variables. The particles really don't decide their state until the moment of measurement. The connection between them is real and instantaneous. It's as if the two particles, no matter how far apart, remain a single quantum system. Measuring one part of the system immediately affects the other part. We can't use this to send faster-than-light messages because the outcome of the measurement is always random. But this spooky, non-local connection is a fundamental feature of our universe, and it's being explored for new technologies like quantum cryptography and teleportation. After a journey through particles that are also waves, a universe that is fundamentally uncertain, and spooky connections that defy distance, you might be wondering, what does all this strange science have to do with my life? The answer is, a lot. While the theories might seem like science fiction, their applications are all around you. About 1/3 of our entire economy is based on technologies that came from understanding quantum mechanics. The world we live in today would be impossible without it. The laser in your Blu-ray player, the checkout scanner at the grocery store, and the fiber optics that bring you high-speed internet all work because we understand how electrons and atoms jump between energy levels, a purely quantum effect. The transistors that are the building blocks of every computer, smartphone, digital camera are quantum devices. They rely on controlling the flow of electrons through semiconductor materials. Even medical technologies like MRI machines, which let doctors see inside your body without surgery, use the quantum property of spin in the nuclei of your atoms. And the future is even more exciting. Scientists and engineers are using these mind-bending principles to build the next wave of technology. We already talked about quantum computers, which could revolutionize medicine by designing new drugs and materials. They could also help us create better artificial intelligence. Then there's quantum cryptography, which uses the principles of entanglement and the uncertainty principle to create unhackable communication channels. Imagine sending a message that is perfectly secure, because the very act of a spy trying to intercept it would change it and alert you. So the next time you use your phone or watch a movie, remember the strange and wonderful quantum world that makes it possible. This realm of uncertainty, duality, and spooky connections isn't just a curiosity for scientists in a lab. It is the fundamental operating system of our universe.